purpose of codec projects, and also how the workload, which is a bit of a more subjective issue, that remote tower will differ from the ones in a conventional tower, is the purpose of a CapMod project. So the first problem of how to optimally assign airports to remote tower positions, remote tower modules, was formulated as integer program with the following constraints. So first of all, we want to limit the number of airports controlled from one position. To the best of our knowledge, currently only single operation is deployed worldwide, which means that only one airport can be controlled from one controller position. But what's unique about remote towers, it actually allows multiple operation. More than one airport can simultaneously be controlled from one position. And this is what we try to explore. And this is a parameter of our optimization. We can change it from 1 to 3 or more airports from one position. And we also limit the number of movements or arrivals and departures from one controller position. We also looked deeper into how the shifts of remote tower controllers actually organized, how much time they spend in position actually controlling, and how many breaks they need, how often they need to break. And also we looked into very important issue of endorsements. What is how many airports each remote tower controller should be trained for. And of course, what's special about remote tower operation, that it's 24/7, unlike the conventional small towers. And this is just an example how our solutions and output can look like. Of course, as any optimization work, we play with different objectives. Here we want to minimize the average number of controllers per airport, which will minimize the number of airports to train controllers for. And for one day of high traffic in 2016, you can see assignment of for 5 airports to the controllers. So here you see in the rows, you see airports, and for one day of operation, every hour of operation, we assign controllers to work in these airports. The colors actually represent controllers' shifts. And as you see, some of the controllers actually are assigned to work on 1 or 2 airports. So we limited the number of airports to 2 in this particular setup. And the number of movements is up to 10. This results in this kind of assignment, and in the table in the middle, you see the actual controller shift lengths and breaks are the white spots. And this results in 8 controllers needed to cover 5 airports. And in average, we need to train them for at least 2 airports. And we also looked at 2 weeks rosters, longer rosters, and adding all the constraints on the weekends, nights, and time between the shifts. We end up with 17 controllers needed to be employed in a remote tower center for 5 airports. This kind of modeling, which is described in detail in the paper, which is given below, helps us to evaluate RTC efficiency. So how a remote tower can save the cost, so how much we can save on human resource. Here you see the results for one day of operation in October 19. If we need to staff 5 individual airports, small towers, we need at least 17 controllers for that day. And the same 5 airports can be controlled from remote tower with only 8 controllers. And adding a buffer, the natural buffer of 33 to 45%, which gives us flexibility for people to get sick and go on vacation, and also paternity, maternity leaves, will end up in 26 to 34 controllers at individual towers and only 12 to 15 at remote, which gives us quite a significant savings from 42 to 55%. Then we ask ourselves the question, can we do any better? Can we still continue optimization and save some more things? But for that, we actually need to look deeper in what is the input to our model. Previously, we looked only at the scheduled EFR movements, arrivals and departures. But what's inside the optimization is actually the so-called mental workload. This is what we distribute between controller working positions. And this is some subjective measure, which is limitation of the number of tasks controller can perform. And unfortunately, there is no single generic metric for that. And this is what we challenge in our project, capacity modeling for controller workload evaluation, which Christiana will introduce you into our recent results on that.
Yeah, so as Tatiana said, we wanted to figure out how can we include the controller workload into our optimization framework. And so the question that we asked ourselves for this project is first, which factors contribute to the controller's workload? So which factors drive the workload of a air traffic controller? And then in particular, if we look at the workload of a controller working at a remote tower center and at conventional tower, how does that differ? And then finally, we also wanted to see how other factors impact the workload. And in particular, we wanted to see how different weather conditions, so different intensities of different conditions like snow or convective activity, influence the controller's workload, and in what way can we integrate this into our staff scheduling framework. So I will give you an idea about how we answered or went towards answering the first two questions, and then Tatiana will take over for the third. Tatiana already gave you a link for one of the papers. So if you're interested in any more of the work, we'll give only a brief recap of that. On the very last slide, we'll provide you with a QR code that just take a picture of that, and that will lead you to all the papers and the presentation, sometimes also videos if they exist. So if you want to learn more. So let's go into answering the first questions, but first let's look into what kind of methods did we use to actually answer those questions. For one, we looked at simulation and analyzed data that we obtained from simulations. And on the one hand, there was simulation data that we kindly obtained from our colleagues at DLR, and we together analyzed that data. There was some older simulation data. We also used Sundsvall validation trials data, which our colleagues from LFV kindly provided for us, and that was recorded in May and June of 2019. If we think about the second question that we asked, we wanted to see what's the difference between the workload at remote tower centers and conventional towers. So how do we go about getting the conventional tower data? Well, we actually did a field study. So we observed and collected data under operation at Bromma Airport in March 2019. We did video recordings, audio recordings, but we also questioned the controllers on their subjective workload ratings, and we analyzed this data together. So what are we aiming for? We do a mathematical analysis looking at both the subjective and the objective assessment. So we on the one hand have the workload rating by the controllers, and on the other hand, we have quantitative measures that, for example, come from eye tracking or the video analysis, and we try to see what kind of connection we can obtain. And the first thing that we wanted to do, so going back to this first question of what drives the controller workload, we wanted to identify complexity factors influencing the controller workload in remote towers. So for that, we used the simulation data set provided by DLR. There were 12 Atcos working in pairs, and always one was actually actively working as a controller. The other was observing and assessing the workload of the active controller. The simulation was run in multiple operation with 2 airports controlled simultaneously. And to assess the workload, we used the adapted Cooper-Harper scale, which you can see on the right, where we're in particular interested in those ratings that we deem critical in terms of safety. So that means that the situation can only be handled by the controller either with reduced situational awareness or it's impossible to handle. And our aim was to identify the critical complexity factors that drive the workload for our controllers in the remote tower. And for that, in particular, those kind of situations where we have something happening at the 2 airports simultaneously that will result in a risk. So how do we go about that? Well, we aggregate our information. So we look at pairs of events and later also at triples of events to see what happens at those 2 airports. And then to analyze that, we looked at 2 types of controllers. So one is a mean controller rating. That is, we assumed an average controller, and we say, okay, this is either manageable or unmanageable for our average controller. And of course, we know that whether a specific situation is actually manageable or unmanageable depends on various factors, on the experience of the controller, the age, various others, but that's the mean version of looking at that. We also looked at a more conservative rating. We looked at the maximum controller rating. That means we considered a situation as critical, even if only a single ATCO rated it as critical. So we will definitely identify all critical factors. We will be very conservative because it can really be only one, but we will also make sure that we exclude what is unmanageable for any controller if we take this into our planning, if we exclude these kind of situations. So what are the results? We identified 65 event pairs, which are listed at the left-hand side of this chart. And for the mean controller rating, 17 of these event pairs were identified as critical. And so they are above this green line, everything that is in red. What we can see is that the complexity increased if the controller has to work with a traffic conflict at one airport and some other task, some routine task at the other. So if we look at these 17 critical event pairs, 9 of these 17 event pairs were actually having a conflict at one of the two airports. Then if we look for the maximum controller rating, of course, we will identify more critical event pairs, and actually 31 out of the 65 event pairs turned out to be critical. And 5 of them have a maximum rating of 10. So where at least one controller said this is impossible to handle. So this is our work towards identifying those factors that influence the controller workload. The next thing we were aiming to identify what's the relationship between subjective workload ratings and several quantitative measures. So we looked at the number of controller tasks, which you can see listed at the bottom of this slide, and other measures related to communication lengths. And then we wanted to validate those quantitative indicators on their power to actually predict workload, both in a conventional tower, in a remote tower, and in a remote tower both in single and multiple mode. And when we say validation, we do not simply mean correlation analysis, but we actually lean heavily on mathematical notation. So we borrow something that's called a necessary or a sufficient condition. And I'll tell you more about that when we actually look at some results. Before that, I would like to tell you a bit about what kind of data we used for that analysis. So as I said on this first slide of the method that we have, here we used a simulation study from the Sundsvall validation towers from 2019. So it's a simulated remote tower. The 3 Atcos rated their workload every 3 minutes. We use the ISO scale here, so that's a scale from 1 to 5. We have 3 cameras from which we do video recordings, and from these recordings we obtain the controller towers, the communication times, and also other measures like the reaction time to spam queries, which we'll not look into detail in today. And then, because we also wanted to look at conventional towers, we did a field study at Bromma Airport. So that happened during actual operations. We used the adapted Cooper-Harper scale again here to assess the workload. This is more fine grade. We have a scale of 10. So our hope was to see if we can find certain fluctuations that we cannot perceive with the ISO scale. We used 5 video cameras. So there were 3 facing the Atcos and 2 the runway ends. From the video analysis, we gained the Atco task. And during our 4 hours of operation, we had a quite varying intensity of the number of movements. And we started with 4 movements in the very first hour and had 27 movements in the last hour of peak traffic. We have 3 Atcos, we have the audio recordings, and what we have, which we do not have in simulation, we have actually weather. So this is in Sweden, so we had snow sweeping appear quite heavily in the first 3 hours. Okay, so let's look at some results. This is just one chart from the simulation study in multiple mode. We have the 3 controllers. In yellow, you can see the development of the controller workload, and in pink, the number of controller tasks, and the others are measures related to the communication duration. So I told you we take mathematical notation, so we use necessary conditions. What does it mean? A measure is considered to be a necessary condition criterion for workload rating increases if every time that we observe a workload rating increase, also our measure increases. On the other hand, it would be a sufficient condition if every time that our measure increases, also the workload rating increases. That would mean we can only look at the measure, don't have to observe the actual workload, because we know if this one increases, the workload will increase. And we can define the same thing for decreases. And then, of course, if we could have a measure that is a sufficient criteria both for workload rating increases and decreases, we would have our wonderful, perfect quantitative workload predictor. Okay, we're not there yet, but we could observe a necessary conditions. And that is every increase in workload rating was always accompanied by an increase in at least one of the duration of communication during that time interval, or the sum of the average communication duration weighted Atco tasks for 2 consecutive time periods. We look at 2 consecutive time periods because controllers already anticipate tasks, and so that proved important to take into account. Okay, so let's look what that actually means. We'll look at the pictures. So here we have a workload rating increased, and that's accompanied by actually an increase in both the blue and the gray measure. Here we have a workload rating increase. The blue measure decreases, but the gray measure increases. Oh, that was one too many, sorry. So at least one of. And then we look at this workload rating increase between 21 and 22 there at the Atco 1. In this case, the gray measure decreases, but the blue one increases. So we always meet this at least one of the 2 measures increases. And one important thing to remember is that the number of Atco tasks is not a necessary condition for an increase in workload rating. And from all that together, what we got, so valid for both the simulation studies in multiple and single mode and the field studies, is that an Atco workload rating increase is always accompanied by an increase in at least one of these 4 measures, which are all related to the communication time, and 3 of them also take the Atco tasks weighted with some communication time measure into account. And of course, it's a bit, well, should we take it like that, or can we maybe come up with a combined measure? So there is still some research needed to be done. But what we get is from this necessary condition, we get an insight into the workload development. And of course, as I told you before, the goal would be to have a sufficient criterion both for workload increases and decreases, because that would yield a quantitative workload predictor. And with that, we'll move over to the last questions on weather, and I'll hand back to Tatjana for now.
Okay, so the last question which we answered in this project was how the weather actually impacts controllers' workload. We noticed that during the field studies at Bromma, when we observed these snow sweeping procedures, a very large part of the communication duration in the communication split was devoted to ground communication, and this was due to snow sweeping. During the first 3 hours, controllers rated their subjective workload much higher, despite the fact that the number of movements was quite low. Unlike on the last hour when it was no snow, but very large amount of aircraft movements, they rated their workload lower in the average. So this was an interesting observation and gave us motivation for further studies of the weather. And of course, in general, everyone who has ever been to the tower knows that the weather actually changes how the controllers work. It increases the communication to the ground and to the cockpit. It also results in more frequent out of the window observations and can change the arrival and departure procedures and routes. So concerning staff planning, what we learned is that in conventional towers, staff adjustments actually never happen due to weather predictions, which should not be the case in remote towers. And we think this question is very urgent to be addressed, as we can end up with some overload or unmanageable workload for controllers who work in multiple operations, who will have some problems with the weather in one airport. And even if another airport is not experiencing bad weather, controller needs all his attention to the one with the bad weather. So our research questions are how different weather phenomena impact controllers' workload, how to quantify this impact, and how to integrate this impact into our RTC staff scheduling, which will definitely contribute to the safety assessment of multiple operations in the future. We proposed a very simple first strategy to address this question. We identified the impactful weather phenomenon at each considered airport and also look at threshold values when to consider this weather to be impactful. We get weather forecast in the form of EPS, the typical meteorological product, and then also combined with flight movements from historical data, we calculate the distribution of the necessary number of controllers with respect to the weather events. So for our experiments, we took 5 airports in Sweden, which are either already remotely operated or planned for remote operation. They are geographically spread around Sweden, so just to cover different climatic zones, and the size of airports is from low to medium. We interviewed several controllers who have significant experience working at these towers, and 2 of the 3 controllers actually already work remotely, which gave us quite a good knowledge base for our results in the interview questions from the interviews. So we asked them multiple questions related to the weather, and in particular, we concentrated on a number of tasks which controller actually can experience due to different weather events. These tasks may include anticipation and detection of the weather, visual observation, arrival clearances on holding areas, increased frequency, occupancy time, and frequent meteo updates. The controllers answered in rows, yes, no, rarely, maybe, often, and we quantified or translated into numerical values as shown in this figure. And so having these average controller ratings over task load or the tasks, additional tasks associated with each weather phenomena, we have this kind of results, which are heat maps, so-called heat maps for different weather intensities. So we look at 5 different weather conditions: snow, precipitation, low visibility, strong winds, and convective activities, which are actually typical in Sweden. And then we get this kind of heat maps for each weather intensity, light, moderate, or severe, for our 5 airports. And if you remember, the spread of airports was from north to south, which means that, for example, the snow was mostly experienced in the northern airport, which is airport 1 and 2. And you see the impact of this is higher rated by the controllers, while convective activity in the opposite is mostly typical for the southern airport, and it's a large airport, I mean, medium-sized airport, but larger in comparison to the previous ones. And the controllers rated the impact of convective activity higher, even in a light occurrence of this type of weather. So having this in hand, these results, we enforce additional condition to our previous framework, which we developed for controllers assignment. So we add a constraint for the requirement of a single operation. So the intuition, the idea is very simple. We want the airport which is experiencing bad weather conditions to be controlled in single operation by only one controller who can concentrate all his attention to this airport. So again, we work on our optimization framework, which is implemented as a mixed integer linear program, and it's solved using AMPL Gurobi solver on a very large, powerful tetralit server provided by Liu Facilities SNCC. And here's just an example results from our experiments. We look at one winter weather day and one summer day when a combination of several weather happened. And if we don't take weather into account, as in previous scheduling, we see only 5 controllers is needed. But when we actually take this impact of the weather into account, we may end up in the worst case with 8 controllers, or 6 or 5, but definitely more than 5 is needed for each of these example days, depending on the cutoff value, which is a choice of operations, which defines how to define these impactful weather events, which weather to consider impactful to which extent. So in conclusion to this work, I can say that in this experimental part, we just gave an example demonstrating that ignoring weather can lead to understaffing at remote towers. we proposed a simple strategy, which of course can be and will be enhanced, and we need to model the weather properly. And we also emphasize the need of development of the weather products linked to this kind of staff planning problems. And now I pass back to Christiana to give final conclusions of this presentation. Thank you.
Okay, so let's briefly summarize the research questions that we had. So for answering how we can organize the human resources and how we can distribute the work at the different airports to the controller working positions, we designed an optimization framework to construct optimal shifts, for example, with respect to the number of controllers and also looking at other objectives. Then we wanted to look at the difference of workload between the remote tower environment and the conventional tower. So the first question was, which factors contribute to the controller's workload? And there we looked at the critical events, both from the average controller rating and the maximum controller rating. The next question was, how do we look at differences, or can we see something that's similar for the remote tower center and conventional towers? So we looked at simulation data and had video recordings, and we had a field study at Bromma Airport, and then analyzed that to see some necessary conditions for workload rating increases. And finally, as you just saw, for our last slide from Tatjana, we have different weather conditions, and we wanted to see how they influence the controller workload. So we interviewed controllers, and with that, we obtained an impact on the different tasks. How many tasks do we get additional, and then defining by the cutoff from the operational requests, we have these higher numbers of controllers that are necessary because of weather. And with that, I would just briefly come to future work. So we continue the study of controller workload and fatigue in RTCs, in particular with our colleagues at LFW. We would like to transfer our framework to en route traffic, and we actually just started a project with similar goals for train dispatchers, so taking this to a different area, and we're of course always open for new ideas and collaboration. So thank you so much for your attention. There's a promised QR code for access to all the papers and videos and slides, and we look forward to your questions.
Thank you so much, Christiana and Tatjana. That's so wonderful insights and so interesting research. I'm sure there are so many questions that are popping up on our screens, and that we'd like to have after the all the speakers have finished. The human factors actually have always been a gold mine for research in air traffic management. But with the advent of digital tower, it's no more a digital tool for air traffic controller which you have to evaluate. It is the entire digital environment in which air traffic controller are operating now. So there is a need to have a fresh look at the human factors related question, and I think your research gave an excellent insight into that. So our next speaker now is Dr. Zena Lu, who is a research fellow at the Saab and TU Joint Lab, where she is investigating the human factors issues in multi-remote tower for the air traffic controller in the Saab lab. Her research explores the usage of eye trackers and EEG as a less obstructive and more objective alternative to subjective survey for human performance assessment. Zena holds a PhD in cognitive psychology and neurosciences from the National University of Singapore, where she developed new models and algorithms about how humans differentiate short-time intervals and cognitive mechanism, resulting in temporal decision biases. In today's presentation, she is going to present her research about how attention switching between multiple towers can contribute to the workload of the air traffic controllers in a digital environment. Zena, the floor is yours. Go ahead.
Right. I'm going to talk about the impact of attention switching on workload in multi-remote tower operation. So in the conventional single remote tower, especially in a low traffic airport, sometimes there are just not enough aircraft to keep the controller fully engaged. And this will sometimes result in the out of the loop phenomenon. And the MRTO would could actually strategically combine such airports together so that a controller could have a more stable workload. And as a result, it can improve the situational awareness of the controller, and not to mention that it also offers a better cost efficiency. But all of these benefits come at a small cost. So it's also possible to overload the controller, and it's also possible to cause confusion. That's why the operational safety has always been the top one priority in the MRTO research. And there's some selected findings from all of the research studies. And all of these findings agree that there are no safety issues found in the MRTO experiments. But there's some issues that I want to highlight. And different studies rely on a different ATC task. So when you find that simultaneously doing a landing task is safe, can we generalize to a different set of tasks? Can we say the same for maybe a conflict detection task? It's harder to do so because just now the two speakers have told that different tasks have a different level of complexity. And there's another point. So some studies are comparing a simultaneous task across 2 to 3 airports to a sequential task performance in these different airports. But it's very hard to specify the definition of simultaneous. So the time gap between a consecutive task is a bit vague. And when you're comparing simultaneous versus sequential task performance, and simultaneous condition will always have a higher task load. So when you observe a higher workload in the simultaneous task condition, can you claim that all of the change in workload result from task load alone, or are there other factors other than the task load change? So in our study, we want to keep the task load constant and to see whether the other factors could affect the workload. And there's another issue I want to talk about. When we say that there's no safety issues in MRTO, does it mean there are absolutely no issues at all? Or does it mean there are some hidden issues that we haven't discovered? So human behavior does not arise from nowhere. Firstly, we must select information, select the most relevant stimulus from the environment. And next, we are going to process the selected information. And last, we are going to make decisions and have performance. So if the two stages are flawless, when you could select the most useful information and you can process the information very efficiently, we can probably predict good performance and good decision making. But when you could not observe any performance decrement, can we claim that the first two stages are still perfect? No, it's harder to do that. So even though we couldn't see any overt performance changes in MRTO setting, but can we claim the same about the first two stages? How about the visual attention selection and information processing? So this is the approach we are going to adopt. And we're going to start from the first level, visual attention, and we will use eye tracker to study visual attention, followed by EEG to study cognitive processing. And lastly, we're going to assess the task performance. And it's very important for us to look at the first two stages all together with the behavior. It's because ensuring safety is really the bare minimum we must achieve. But if we can pinpoint the vulnerability at different stages, and we know more about the first two stages, we could actually not only make the controller more resilient to possible risks, we could, in fact, make the controller perform even better in the MRTO setting. So one of the such risk factor is attention switching. So it's quite intuitive when you're having multiple airports. More airport means more aircraft, and more aircraft means more visual stimuli. So it's not hard to know that it's even more challenging for the controller to select the useful information from a more crowded visual scene. And the controllers need to consciously think about when to pay attention to which airport. That's why we are going to investigate the impact of attention switching on workload. And in this study, we're going to use a very simple landing task. And the factor we are manipulating is the frequency of the switches. In the first level, so one aircraft is going to land in airport A, and next is going to land in airport B. So in the second condition, the frequency decreases. So it's AAAA followed by BB. And the last condition is the easiest. So the switch only happened after 4 aircraft. And in this task, we're going to use eye tracker to look at the pupil dilation, to look at the visual scan path. And in the future, we plan to use an EEG to study the frequency of some neural oscillations. And this is the eye tracker we are using. It's a head-mounted eye tracker so that controller could actually move his head around when he's doing his task. And there's one scene camera that's going to capture 100 degrees of field of vision, along with 2 binocular eye cameras that are going to record the eye movements. And this is our experimental setup. These markers are for surface detection. So in our experiment, we have defined quite a few surfaces, but for the initial analysis, we only use the first 2 surfaces corresponding to 2 airports. For the initial analysis, we didn't use the E-strip surfaces. And in the second figure, the red dot is actually the detected gaze of the controller when it's overlaid on the detected surface. And I'm going to show a very short video clip of the controller preparing for the task. And the number next to the gaze is the fixation count. So even before the aircraft arrived, the controller has been quite busy scanning across the 2 airports and the E-strip. And I'm going to show some of our preliminary results. So this is the rating from the ISA scale. The controller needs to rate his workload level every 3 minutes on a scale of 1 to 5. He didn't really experience a big difference across these conditions, but if you look closely, ABAB has a slightly higher workload score, just that it's not so obvious. And here are the results from the eye tracker, but we couldn't really see a big difference in pupil diameter and blink duration. And this is the attention switching result. So when the first gaze enters surface 1 and the next gaze enters surface B, it was defined as a switch. So when the first gaze enters airport 1 and the next gaze enters the same airport, it was defined as a repetition. So even though across the AAA and ABAB, we do see a different pattern, but the pattern is a bit different from what I expected to be. Partly is because I didn't include enough surfaces to look at the scanning behavior. And for our study, we've only used 1 controller, and it's not enough to generalize the result to other controllers. And we didn't break down the data based on different events. So when a controller is doing random visual scanning, and when he's looking at an aircraft, all data points were aggregated together. So that partly explains why the results, from my results, I didn't see a big difference. And so for the next follow-up analysis, I'm going to include more participants and do a more refined event-related analysis. And I'm probably going to define more surfaces, including the radar, the E-strip, so that whenever the controller is shifting his gaze from the E-strip to the airport, it means a different thing when the controller is looking maybe from shifting his gaze from the airport to radar. But those of the events are not detected in my initial analysis. And I'm going to conclude my presentation with a slide. So there's just one point I want to highlight is the workload measurement. So just now I've only talked about attention switching. So it's also very important to for us to derive a task agnostic measure of workload using not just self-report, but also eye tracker and EEG. It's because self-report is not only obtrusive, it's very subjective. So it kind of assumes the controller know how tired he is, but sometimes he might not be so aware of how he feels. And in the future, we also want to correlate the results from the EEG and eye tracker results with the behavior changes for us to know how much changes we see in the eye tracker and EEG data could predict a behavior change for us to observe. Yeah, that's everything I have. Thank you very much.
Thank you, Dr. Zena. That was so interesting. Actually, Zena enlightened me as a cognitive neuroscientist once that humans do not do multitasking. There's nothing called as multitasking for humans. We do quick attention switching. That we confuse ourselves as a multitasking person. So this was the basis of the research that we started understanding how humans, and in particular air traffic controllers, switch attention between multiple tasks and come up with the issues related to the multiple remote tower. For Zena, we have so many interesting questions. I think we'll be taking them very soon. But before we do that, we are going to dwell into more of a virtual environment with Dr. Pallavi here. So Dr. Pallavi is a research fellow at the Saab NTU Joint Lab in Singapore, and she's investigating mixed reality systems and interaction design for the air traffic controller. Her research explores the possibility of using different human inputs to interact multimodally with the mixed reality-based air traffic control system. Dr. Pallavi is a specialist in computer graphics, 3D animation, and rendering. She did her PhD in human-computer interactions from NTU Singapore, and her research area was multimodal human-computer interaction design for virtual reality system. So Dr. Pallavi, the floor is yours. We look forward to hear some very interesting talk from you. Go ahead.
Thank you, Professor. Okay, so hello everybody. My name is Pallavi. I am a research fellow at Saab NTU Joint Lab, and today I'm going to be talking a little about the research area that I have been working on the past few months, which is on embodied multimodal interaction with a portable mixed reality-based digital tower. Now, here's an overview of what I'll be talking about, starting with the state of art in digital tower and some of the present challenges that they face. We will then talk about how mixed reality, my research, comes into the picture, detail the system design of a proposed system, talk of some early studies and preliminary validation results, and some of their key outcomes. Let's start with the state of art in digital towers. So ATC towers have come a long way from conventional physical towers to remote digital towers that have dedicated displays at a separate location. Now, such digital towers offer a single shared out-of-tower view, but the issue here is that controllers need to look down at their individual displays for additional information, which in turn has been shown to decrease their situation awareness. We know of this as the hit down time, and we have been actually on an eternal quest to reduce this time. Presa Retina is a 2018 project that you can see right here. this has actually actively explored using both virtual reality and augmented reality to provide a conformal visual representation of this out of tower view, along with some relevant information overlaid on it. So this was their proposed solution to reducing the head down time for controllers. But such a system actually comes across with a few additional challenges. This includes increased physical workload and overlaid information clutter on the out of tower view. Now, since controllers do not have a separate system to look down for additional information, all available information in such a system, SSR Retina, is presented on a single screen, which actually detracts from the out of tower view. Other digital tower systems in literature, as well as the industry out there today, only have very limited interaction support with basic menu-based interactions, which in turn, again, detracts from this out of tower view. So after a bit of study on the state of our digital tower systems today that use innovative platforms such as VR and AR for air traffic control, we compiled a list of challenges we've identified. So these are the few key issues which have been summarized here. Number one is that platforms such as VR headsets largely offer very limited field of view and visualization options, since such devices are not generally geared towards safety critical operations such as air traffic control. In addition, in a VR headset, you are actually cut off from the rest of the environment, and you cannot see your co-workers or your other air traffic controllers while wearing it. Second, the less head down time, the better, always. But this shouldn't be coming with some associated drawbacks such as visual clutter, which brings me to the third issue, where all available information is overlaid simultaneously on a single view. Another pertinent issue is the lack of intuitive interaction methods. The available interaction methods we see are mostly point and click based. Now, we believe that some amount of visual clutter can be reduced by interactively selecting or deselecting information and giving the controllers an ability to choose whether to hide or show certain information according to their context, where they're looking at, what the situation is, etc. Which brings me to a very pertinent question. How can we develop a system that addresses such challenges while also removing the need for massive spatial displays altogether? Now, the answer might lie, quite surprisingly, in mixed reality. But that's not all. When it comes to very new platforms such as MR, VR, and AR, we have to ask ourselves, how do we alleviate the unfamiliarity for controllers to adopt to new interfaces to perform very intensive cognitive tasks? It's enough to get used to a very novel platform and to learn all the various controls associated with it. But how do we smoothen this transition? It has been studied that immersive visualizations of air traffic increase situation awareness, but such immersion cuts the controller out from the outside world, as I had mentioned earlier, and limits their collaboration. Mixed reality supports a see-through immersion model. In such an air traffic system, you get an immersive view of the runway with integrated data overlays while you maintain your view of the outside world so that you are not cut off from whatever is happening outside. Now, what's also interesting is that in a mixed reality MR system like Microsoft HoloLens 2, there is also the possibility of it providing a self-contained digital tower system to visualize only relevant information to the specific controller. Now, this was another question that we asked ourselves when we reached this stage. How can the interaction capabilities of such a headset, such as Microsoft HoloLens 2, or such a platform like mixed reality be used to offer a natural and interactive experience for controllers? So the research that I do here that attempts to answer this question that I asked envisions a mixed reality-based portable remote digital tower system that has embodied multimodal interaction capabilities. Now, embodied basically means using one's own body to interact, your hands, your eyes, any part of your body, and multimodal combines two or more interaction modalities or human input methods. To do this, we basically developed a simulated 3D digital tower environment in mixed reality using Microsoft HoloLens 2. You can see a picture here. We added several visual features from real-world air traffic control environments to be visualized in mixed reality, but it is still a simulation. We also incorporated interactive capabilities to them, specifically to aircrafts, gates, and runways. Now, what we intended to make was a prototype of a possible real-world system, and as a very preliminary way of making sure that this is the right way to answer the question that we asked. So this is the concept of such a system. The view from the remote tower is visualized in mixed reality using Microsoft HoloLens 2 and Unity. Key controller tasks were identified and mapped to hand and eye gestures using a multimodal interaction design model, which I'll get to later, which fused to form interaction gestures. The visualization and interaction model are then combined to form this interactive digital tower system in mixed reality. So this is an overview of the concept of the system and how the different conceptual components interrelate. Now let's look into more detail about a bit of how it's been made. Here's an overview of the design of the system. You can see on your right how the various hardware and software components are connected. For hardware, we use Microsoft HoloLens 2, which comes with many different embedded sensors that track human input. This is also probably the first mixed reality device available for industry applications today. The device has embedded eye and hand gesture information sensing in it, which is then tracked by our system and then processed by the multimodal interaction model that we have designed. Later, we deploy the application to HoloLens using Unity with the added visualization plus interaction capabilities. So this is a sort of overview of how the hardware and software components interrelate. Now, let's look into the interaction design model of this. To design the interaction model, aircrafts, runways, and gates were identified as interactive targets with these functionalities embedded within them that you can see as a list. View basic and detailed aircraft billboard. Now, a billboard is, you can see in the picture here, a tag attached to an aircraft with varying levels of information. So they are interactively called upon. So if you look at an aircraft, for example, you can see the basic view of a billboard for both arriving and departing aircrafts. But if you want to see more details about the aircraft, you'll have to use hand gestures to bring up the detailed view of the billboard. I will explain more of these gestures later. The other functionalities include viewing routes, distances, flights on a particular runway, and flights approaching a particular gate. Now, we designed a multimodal interaction model that fuses eye gaze and hand gesture, the where what model. Now, this was inspired by a real-world physical interaction with an object. The user's eye gaze specifies the where. For example, the user looks at a particular aircraft, and the hand gesture specifies the what. For example, the user performs a hand gesture that means show detailed billboard of the aircraft that I'm looking at. This is an example, a couple examples of what I mean. The model was then mapped to interactive targets in our system, aircrafts, runways, and gates. So controllers can use a combination of eye gaze and hand gestures to perform a lot of different actions, as you can see in the picture here. So eye gaze calls upon the basic billboard of only the aircraft that you're looking at. A combination of eye and hand brings up the detailed billboard, route, and distance. Hand gesture alone on a gate or a runway highlights the relevant flight approaching the gate or the relevant flight approaching the runway. So we built this very early prototype of it, and we wanted to get a feel of what controllers, actual air traffic controllers, think of our system, wearing it, using it, just playing around with it. But other than that, we decided to go for a formal evaluation, but it was a very early study, a preliminary validation of the MR-based system for general insights and feedback. The aim of the system was to get initial feedback of controllers' perceived usefulness of system as a viable augmentation of a remote digital tower system, and also to validate the effectiveness of the several interactive features in the system. The participants were 3 licensed air traffic controllers, 1 former. The methods used were think aloud protocol and while doing the study, and a post-study semi-structured interview, which asked for participants' verbal feedback on the following components: system trust, confidence and understanding, system usability, air traffic control applicability. So some of the initial results are shown here. In a user perception interview, controllers verbally rated the system highly in terms of trust and confidence. However, they felt they needed some additional training to be more confident in using it. A thematic analysis of their Think Aloud protocol during the experience gave us some very useful insights and feedback on improving the system. And we understood how it really added value to the controllers' day-to-day operations. For example, controllers agreed that interactions were useful, and in particular, eye gaze really helped with visual clutter. They also identified some very specific situations where such a system would be particularly useful, such as low visibility conditions or nighttime operations. They believe that with adequate redundancy, it can replace physical towers, and that its primary selling point, so to speak, was mobility or the lack of reliance on a physical location. Overall, they agreed that despite the novelty of the mixed reality platform, it shows a lot of potential as a possible augmentation of the current digital tower systems. However, a bit of limited training would be necessary for controllers to be initiated into this system. Now, these results gave us a lot of early feedback and insights to guide our future system design, and we're very confident of taking this forward into a fully fledged working air traffic control system in the future. To summarize, the key outcomes of this research project thus so far are a visualization of air traffic in mixed reality, which is simulation, a multimodal interaction design model embedded within it, and a preliminary evaluation with controllers who perceive this system to be a promising and useful way to augment information on a digital tower system. Now, in the long run, this research aims to develop a completely viable alternative to the present immersive digital tower environments in the form of a self-contained, richly interactive digital tower system in mixed reality space. We also plan to conduct more extensive user evaluations on controllers using this real-time system and do statistical analysis and quantitative analysis on the data that we receive to form stronger conclusions. But with this early prototype, we find that we're a bit along the way towards our vision already, and we hope to make it all the way to this goal very soon. So yes, this concludes my presentation. Thank you very much for listening. Thank you.
Thank you, Dr. Pallavi. Very interesting talk. It took us into a really virtual world. And I believe this will allow controllers to work from home one day, right? So we got so many questions actually, and I would like to open the floor for questions. May I ask first questions on behalf of our attendees from Tatiana and Christina. There are lots of questions. I might be not able to take all of them, but please assure that I will email your questions to the respective speakers so that they can answer and the answers be available to you. So one of the questions which is recurring being asked was about how we can benchmark controller performance to determine them as average. The person who is asking is himself is an air traffic controller, and he said that as an experienced controller, I sometimes struggle a lot, whereas new air traffic controllers can perform a task in very efficient manner. So how you are going to determine as an average air traffic controller?
Well, what we said here is really just saying we have the ratings of several controllers, and or maybe I should also highlight briefly that the DLR data was actually designed to go at very high workload levels there, while the data that we had from the simulation studies in Sundsvall and also from Bromma, that was under normal operation, so that we saw very small workload ratings. So what we just wanted to say, we don't say it's about age or experience, or it could be that the new one is doing well better. So we're not trying to insert that. What we just want to say is there is a possibility, if we don't want to be as conservative of saying I exclude everything that is excluded just because even one controller says that this is impossible to handle, you could go for an average, where average is really just, if we look at all the ratings of people that had to rated this situation, then on average, this was rated as manageable or unmanageable. So we're not really benchmarking. We're just saying this is a more conservative way to look at that. A less conservative way, sorry.
Okay. Actually, another follow-up question on the same line, Tatiana, Christiana, is they're asking that given the wide range of subjective even pair complexity ratings, would it be possible or even useful to have a more fine-grained subjective complexity ratings for individual air traffic controllers?
Yeah, it would be very much. So we had that when we discussed the ratings, and we had hoped that the adaptive Cooper-Harper scale would help, but we saw in both things that we saw very little variations, and the quantitative measures that we have showed higher variation. That there could have been, of course, be two things. There could be variations in the measures, and that has no effect on the workload. But the other thing could be that there are also variations in the workload, but we do not have scales that are fine-grained enough to in particular observe fluctuations on low level of workload ratings, so that we can actually perceive that. And so that might also be the goal. If we want to be able to get a sufficient criteria, we might have to first get a better way of assessing the workload rating there.
Okay, another question, same Tatiana, Christiana, because this is a sensitive question, right? This is related to the trade unions. So you can say no comments. So do you have any opinion on how enthusiastically the roster optimization might be accepted by the trade unions of air traffic controllers?
Really good question, but we think we are doing a good job demonstrating them what benefits can it bring to the operations. And we also developed several metrics which show how busy controllers will be. And actually in this remote tower environment, the opposite issue is fatigue. So they always say that remote tower actually helps to fight against fatigue, and controllers are quite happy to be more busy in this. So we think we are doing a positive improvement.
Wow, thank you so much. There are more questions for you, Tatiana, Christina. I will come back to that later, but I am getting more questions for Zena here. Zena, people are asking that some people are in a habit of switching their gaze repetitively. You know, they look here, they look there, they look here, they look there. So this frequent gaze switching, is it sort of a subjective habit that may not correlate very well with the workload? Is it a possibility?
There is a possibility of well, how we search for information does not always align with how we process the information. Yeah, so eye tracker could complement analysis, but doesn't tell us all of the information we need. Like, it's very possible that you are actively searching for information, but you are not able to efficiently process the information.
Possible. Another question that has just came for you is about EEG. So how you plan to use EEG in such a working environment actually? Because this is a very complex environment. It's not a simple environment where you can just use an EEG. There are so many gadgets happening, yes, so many distractions, electrical equipments, and EEG in itself is a very subjective measurement. So how you plan to use EEG in this study? Can you elaborate on that?
Yes, there are a lot of challenges with how to measure EEG activities in a ATC condition, because controllers have to move around, they have to move their gaze, they have to look at the different aircraft, but it's very hard to collect clean EEG data if the controller is moving his body. So, but there's some portable EEG device available in the market, but there's a trade-off of the data quality of the data. So, but it depends on what kind of data you're analyzing. If you're only looking at some EEG synchronization in a certain frequency band, it's definitely possible to rely on this portable EEG device to get some quality results.
Okay, wonderful. We are looking forward for some very interesting findings, which combine both eye tracker, EEG, as well as subjective interview form. Another question that has come for Dr. Pallavi. Dr. Pallavi,
Yeah.
People are asking that in this mixed reality trial, the controller was basically using hand gesture to interact with the mixed reality environment. Whereas in real air traffic control tower or a digital tower environment, the air traffic controller have to do other tasks like flight strip, data entry, weather information analysis, also talking to the controllers and pilots. So do you think this will discount the features of mixed reality environment?
Yeah, that's a very good question. No, I do not think it will, because the purpose of doing these actions using, so what we do here is not using hand gestures alone. We have the eye gaze to assist hand gestures. So hand gestures perform very explicit actions which controllers otherwise do in a physical environment, such as updating the flight strips. So in future, we hope to add the functionality of updating flight strips, etc., information manipulation to the system. So I do not think it will detract from it. I hope it will replace the other things that we do. With respect to voice, I think it's a very critical communication channel, and our system does not touch on the voice aspect of it, as I believe it should be reserved for communicating alone. So I believe that with eye gestures, it can only help controllers achieve their tasks instead of detract from it.
Okay, wonderful. Now this is again a very loaded question. This is because there are very conflicting evidence in the literature about it, about the depth of information.
Okay.
So there's a question about this information, which is layered on the screen in a two-dimensional, and it is less information related to the distance, for example. How do you think this is going to affect the realization of such a augmented reality, virtual reality system, lack of depth?
I think it
Perception,
so I think this same system can be applied to a 3D out of control, an actual tower as well, which will have depth information that you can see, that you can calculate. And in fact, I think that it will add to it. It will provide depth information on screen, which is calculated, so the controllers do not have to gauge it from the visuals as much anymore. Then they could use assisted labels to get the information in screen.
We are getting question for Tatiana Christiana here. Okay, so the question is, in the experiment and the results that we have shown, specifically related to the air traffic controller interviews, there is an effect of weather which differs by the airport, right? So the question they're asking is it due to the airport configuration or more due to the air traffic controller experiences? The effect of weather which differs by airport.
Yeah, I would say that the layout, size of airport, how many runways it has, how many controller working positions, it actually influences what controller experiences as additional tasks. For definitely this is taken into account. So this is why we look at each particular airport. We are not trying to find any average. So we think the impact of weather should be evaluated individually in each airport plan for remote operations. So it should be, and of course, climatic zones. It's very important where this airport is located.
Maybe a brief addition. Also, we were in particular looking at task load. We were not looking at workload. So we were trying to find which are the additional tasks that appear at which airport for which intensity of which weather. So we were in particular not asking how is that perceived by the controllers, but just for the number of tasks that appear.
Yes, I think that Dr. Zena will be also incorporating in her attention switching between different airports, incorporating different weather conditions as well. So another question, Dr. Tatiana and Dr. Christiana, is about the field trial results. Do you found any evidence that the controller are preferring short and frequent communications rather than long and few communication? Did you observe that?
I would say when the traffic level is higher, we observe shorter and more frequent communications in general. So without acknowledgement sometimes, yes, but yeah, in general, they tend to shorten the communication, I think.
Okay, there's a question for Dr. Zena here. This particular technique about using of the eye tracker in MRTO, especially looking at attention switching, what do you think is the future implications of such a research?
Future implication
Yes, on the next generation of digital tower design. Do you think it can go no more than 2, 3, 4 airports? Where do you see it going actually?
It's hard for me to say. Well, I think eye tracker is very useful for us to understand the visual searching behavior of the controller.
Right.
Yeah, so how controller is searching for information basically could tell us how good the controller are going to perform. But it's still not enough for us to make very strong claims about whether like 3 or 4 airports are good, are safe to operate.
Sure,
so we
sure.
need other research techniques as well.
Yeah, we look forward for more airports in the multi-airport environment. Another question coming for Dr. Pallavi here is this is related to the visual fatigue and looking on the screens. I believe some of the controller feedback was about getting the different understanding of the information and not being able to perceive it. So the question is that these screens are very different from the black or gray radar screen which controllers are used to see. Is there any notable fatigue that was observed or indicated by the controller looking at the HoloLens kind of system?
So since our study was limited to time limited in terms of time, they did not report any fatigue, but we will have to do extensive studies. But we believe that using mixed reality, which supports a very see-through immersion system, the screen is not the only thing you see. You also see your real world, and only the content that is basically rendered in the space, the 3D content, is the only form of pixels that you will be seeing. Yeah, in the real world, you can even lift it up to see the screen without the headset getting in the way. So that's the kind of flexibility that such a headset offers.
Okay, so thank you so much. That's fantastic. Actually, we have so many questions and so much limited time. I will just may ask one last question. We have like 16, 17 questions coming on the screen actually. But I will just ask one final closing question to Dr. Tatiana and Dr. Christiana about the use of other data collection methods. I believe you are looking at more of controller feedbacks using questionnaires. Do you have any plans to use other methods like eye tracker, EEG, and other physiological methods for data collection analysis?
Tatiana, do you want? Or?
So the answer is yes. We looked at very different ways to evaluate controllers workload, even some kinetic movements capturing. But the main idea, the red line of our work is that it should be not intrusive. So we are looking at all the measures which are as less intrusive as possible. This is why we conduct with visual observations, and we also work with eye tracking data, but the smart eye devices, which consist of 6 cameras around the controller, and they kind of don't touch him, just observe what controller is doing. So we are looking at all possible ways to evaluate in less intrusiveness. Yeah, it is a main point here. Yeah.
Thank you so much. I think human factor research is one of the major catalysts that is going to transform the research that's being done in the lab on multiple remote tower operation into the field. We are also excited and happy to see 4 beautiful women in aviation leading and pioneering this research work. I would like to invite Dr. Jovis from Saab Singapore to offer the closing comments. Dr. Jovis.
Thank you, Professor Samuel, and thank you all the presenters, especially like our guests and friends from the Linköping University, for Tatiana, Christina, and our very very talented scientists from our lab, Pallavi and Zena. We are really, really happy and proud to have increasing number of feminine figures in the area of research, and this has always been the aim of our lab, is to really promote that. It's very prominent in Europe to promote female figures, but I really, really want to do this also in Asia context. So I'm quite sure that those who are in the sub-NTO joint lab are also happy to have injections of a female figure. So I'm very proud about that. And also thank you very much to Prof. Samir Alam for making this webinar very possible. We are very sad that Sandy can't join us because of the conflict of time, but we were very, very happy anyway that she have agreed to do the introduction, even though she couldn't due to time conflict. And a great thanks to the committee who has pulled these things together. We're proud to have you guys, and thank you for all the participants who have stayed with us throughout the webinar and asking fantastic questions. I'm very happy and glad that we have interested you with our research, and I've listened to the research that's been done both with our collaborator at Linköping University and also at our joint lab. And I'll say, like, we are doing very good research of high quality, very proud about this, and looking forward to a lot more of this good work. And with this, I would like to close the webinar and pass the paper over back to Michael to do the final declarations. But anyway, we will have more of such fantastic events in the near future. So please look forward to it. And I hope that we will be able to see you again to participate in our future webinars. So thank you very much.
Thank you, Joyce. Dr. Mike.
Yeah. Thank you everyone for participating in this sub-NTU Joint Lab webinar series, which we are trying to organize every quarter. So again, to our speakers, and moderator, thank you very much for giving your time and giving us a great webinar. So we look forward to seeing you all in our next event. Thank you so much.
The webinar team, Dr. Yix, Dr. Nimrod, BV, wonderful, Dr. Mike. Thank you so much. Special thanks to Billy from LFE, who actually came up with this idea to have the two teams presenting and exchanging research ideas. So we look forward for our further collaboration. Thanks a lot. Bye-bye.
Thank you all. Have a great day.
Sorry, really, I didn't know you're still online. Thank you.